Good afternoon. Nice to see so many of you. So who was here this morning at my first talk as well? Few hands, okay. So glad to see you back. This talk will be different, although you will also recognize parts back, of course, because it's the same topic. It's about the Java module system. But in this case, we're going to look at how we are actually going to use it and how we can design for it, what pitfalls to look out for. So in a sense, it's a bit more advanced, but we'll start easy. So we'll start with a module primer again, just to get you refreshed on what the module system is all about, what the syntax for modules looks like, and then we'll get into this. Just like in my previous talk, I will be raffling one of these at the end, so please stay tuned. And if you want to have more information, then I highly recommend the book that I wrote together with Paul Bakker as well. There's so much to tell about the module system. We can't fit it in two hours even. But let me get started and we'll try. So in this talk, we're not going to focus on a scenario where we take an existing application and move it to Java 9 modules. You can do that, and there's lots of descriptions of case studies, etc. in the book as well on how to do that. But what we're going to look at today is, what if we forget about the existing class path, and what if we go full in on modules? What would that mean for application design? What would it mean for development in Java using modules? So we want to fully embrace the modules and see what they're capable of. And that also means, of course, that we need to think about what it actually means to be modular in our software development. So this talk is a little bit about design. It's about the constraints that the module system imposes, and also how we can fit existing patterns, for example, dependency injection, into the modular world that Java 9 and later brings to us. So before we get started, I want to do a refresher of the Java module system basics. And what we see here are two module descriptors. And they define the metadata for two modules. In this case, there's a module called easytext.cli and a module called easytext.analysis. If you've been to my previous talk, you will recognize the easytext name. It's a sample application that we use in the book, and I use in this talk as well to illustrate the concepts of Java 9 modularity. And what we see here is that the easytext CLI module has a requires clause in its module descriptor. And this expresses a dependency from easytext CLI to the easytext analysis module. And we see this visualized here as well. And what this means is that the easytext CLI module can now use code from easytext analysis. But it cannot just use all code that's inside of the analysis module. No, it can only use code that has been explicitly exported from this module. So the export statement here takes a package name as argument, and you can have more export statements in your module descriptor. Here's just one. So here we say, okay, the analysis.api package is exported to the outside world, meaning that the easytext CLI module can make use of any code that's inside of the analysis API package. I say any code, and that's not completely true. The easytext CLI module can only use public types that are exported from this analysis API module. So we're very used to using, for example, reflection to break through access control barriers that are in the Java language. And that doesn't work in the module system anymore. And there's a good reason for that. Because as a module developer, you want to be able to actually encapsulate code inside of your module to make sure that only you need to care about it when it changes. And you don't have to think about all the other modules that are using you when you change your internal details. If somehow other modules could bypass this, then you would be in a world of pain again. So that's why even if you export a package, only the public types of this package are usable for other modules. Sometimes that's not what you want. Sometimes you do want to give access to your internal implementation details through reflection. For example, we have lots of libraries that use reflection like Hibernate or Spring Framework or all these kinds of things. And these libraries, they depend on being able to instantiate your implementation classes. Things that you would normally not consider as part of your API, but these frameworks, they need access to this. So for that, there's the opens clause. And opens, again, takes a package name as an argument. In this case, it's a fairly simple package name called impl. And what this means is that at runtime, and only at runtime, other modules can access any types inside of the impl package through reflection. So this also holds for protected classes, for private fields and public classes, etc., etc. All the things that you could do before Java 9 with reflection, you can also do on open packages. Now, normally you wouldn't really want to do this, right? You want to close your module as much as possible. But like I said, there are many libraries in the wild that do use reflection. And if they do use reflection, we need to be mindful of this. And doing opens, in that case, is much better than doing an export of the package. Because if you export a package, it will not only be accessible at runtime for other modules, but at compile time, they can also code against these types in these packages. And that's what you want to prevent. So if you open a package, at compile time, you still can't code against these types that are in these packages. So that's the distinction between open and exports, and we'll see more of that later in the example. Now, when you start working with modules and you have these dependencies with requires and you have the exports statements, you might think that's the end of it, but it's not. If those were the only tools that we would have in Java 9 to do modular development, then we would still have a problem, because if you would actually want to use implementations from other modules, actual implementation classes, they would have to be exported and you would have to require this module to use them. And we're of course used to dependency injection frameworks, etc., and talking to interfaces rather than to concrete implementations, and that's what we want. So to build on our example, let's say that we have two modules, which are sort of front-end modules, EasyText GUI and the CLI. So the GUI has a nice front-end where you can input text and you can analyze it using one of these algorithm implementations. Now, what we don't want is for these CLI modules and these GUI modules to have knowledge of each and every analysis implementation that lives in our system. Because that will be sort of bad. If you want to add a new analysis, then you would have to add a require statement to the EasyText GUI, EasyText CLI. You would have to recompile them, and that's just not really modular and not really flexible as you would imagine it. Now, the nice thing is that with services in the module system, you don't have to do this anymore. So what you can do is you can only share an interface between those consumer modules and those provider modules. But then the question, of course, is how do you get an actual instance in your application, in your CLI module or in your GUI module? Because if you're going to do this, you're going to instantiate some concrete implementation class. That won't work, because to make this work, you would have to export this package containing the implementation, and that's exactly what we don't want, because we would get very tight coupling between those modules. So what we want is we want to only know about this analyzer interface and somehow magically get an implementation or implementations of this interface that we can use in our CLI and our GUI modules. Now again, back to reflection. No, this isn't a workaround in the module system. Even if you wanted to do this, you would have to open the package, as we discussed earlier, and you're still tightly coupled to this concrete implementation, even though you're looking it up by name, which is somewhat looser coupling than directly compiling against it. But still, you have to know exactly about this other module and this other class that lives in this module, and that's what we want to prevent. So services add a layer of indirection. So what you get in the middle, in this case, offered by the module system, is a service registry. And you get consumer modules on the top here, which use these services, and you get provider modules on the bottom here that provide these services to the service registry. And the module system actually wires these together for you. So in this case, the EasyText GUI and CLI modules don't have to require the actual implementation modules anymore, and they don't have to know about the actual implementation classes anymore. They only have to know about a API analyzer interface. And what this looks like in code is like this. So a provider module would require the API module because that's where the analyzer interface lives. And this is sort of the shared contract between the providers and consumers. But then it would say, okay, I, as a module, provide an implementation of this analyzer interface with the Kincaid analyzer class. But as you can see, there's no export statement anymore for the Java Modularity EasyText Analysis Kincaid package. So it's still encapsulated. You can't code against it anymore from other modules, but we can expose it as a service. So this module system, this server system, has special privileges to reach into this Kincaid module and to instantiate this Kincaid analyzer for us. And this way, you can still expose this implementation without having to reveal the actual class that implements it. So this Kincaid analyzer, which is provided, is just a plain Java class. As I said, it doesn't have to be exported, and there's nothing special about this, right? So you do see that you need a no-arc constructor for the service system to be able to instantiate it. There are some other ways to do this, but this is the most used way. And we need to implement our business logic, of course, using the analyzer method. Now, on the consuming side, it looks similar, but different. So what we see here is that we, again, require the Easy Text Analysis API module because it contains the analyzer interface, and we need to code against that in our CLI module and also in our GUI module, of course. But then instead of requiring the implementation modules, we just say to the module system, okay, we want to use any instances of the analyzer interface that you have to offer for us. So this is the metadata that you provide to the module system. And then in code, what you can do is use the service loader.load call. Service loader is an API that has been part of Java for a long time already, since Java 6. Although before the module system, you had to use it using text files in the meta-inf/services directory, and nobody really knew about that. That will change with Java 9 and the module system. It will get a sort of a new life. So the service loader API, if you call load, you get back a service loader object, which conveniently also implements the iterable interface. And we can just iterate over any instances that have been located in the service registry without knowing any concrete implementation types. And of course, this is just a typical inversion of control pattern that we apply all the time, also in systems that use dependency injection, for example. But here, it's a bit more explicit, so we have sort of a service locator pattern going on here. But at the same time, we have the same benefits. We only have to know about this analyzer interface. Now, there's another method on service loader that you can use instead of directly iterating over any instances, and that's the stream method. So when you invoke the stream method, you get back a stream of service loader provider objects. And these are not the instantiations of the actual services yet. No, they're just describing which implementations are available. So you can inspect the implementation class type there, and you can filter on that. For example, you can check whether there are any annotations on it, and you can filter out the one with the right annotation. And then in the end, when you've filtered out the right instances, you can call the service loader provider.get method, and that's when the instance gets created for you, and then you can start using it. So this way you can also be very selective about which providers you actually want to use in your code. Now what this allows us to do is to, in a very flexible way, add and remove modules to a system, which are provider modules, and thereby just growing dynamically the number of available analysis. So this way you can actually extend your application without recompiling or without changing your user interface code or CLI code. And just by adding a new module to the module path, you will get new functionality, and it will be picked up automatically because of the service loader interaction that you have in your code. Now, so far so good, but people often say to me, right, Sander, that sounds very nice, and this pattern really is useful, right, in decoupling modules. But give me back my inject, please. I want dependency injection. And sure, we're going to look at how to do that using Java 9 modules as well. The point is, if we're going away from the service loader API and services, then all the special privileges that the service loader API has, like instantiating these implementation classes for us, they will be gone, right? Because Spring and Juice and all the other dependency injection frameworks are just another library running on top of JVM. They don't have any special privileges. So we probably need to do some work with that. But our end goal is to find out whether we can get the same situation that we had previously using services, only now using a dependency injection framework. And I'm going to use Google Juice in this example. But the same sort of concepts apply to Spring as well, of course, and other dependency injection frameworks too. So our goal is to have these analyzer instances be injected into our CLI code using add inject, and not having to use the service loader API, at least not for our own services. Now, the question, of course, is how are we going to use something like Google Juice in this case? And it turns out that Juice is somewhat amenable to the situation. I'm not sure if you're familiar with Juice, but if you want to do dependency injection with Google Juice, you need to configure this, and this is sort of like the Java configuration for Spring as well. So you need to indicate what are your injectable classes and how do you want to bind them. So what we see here is that in addition to our common analyzer implementation class, we also need to add a abstract module, which is a Google Juice concept. And it has a configure method in which we're going to say, okay, we're going to bind our common analyzer class that's inside of this common module. We're going to bind it to the analyzer interface. And this is very similar to what we declared with our provides clause in the services setup, if you remember. So we're saying here, okay, this common analyzer can be used anywhere where we need a analyzer type. Now, this module will be used later to configure Juice. And what's happening is that consumers of this service now need to somehow instantiate this common module configuration. And also, this common analyzer implementation needs to be in a package that's open, because Juice is going to reflectively trying to instantiate this implementation class, and it can only do that if the package is open. It doesn't have any special privileges like the service loader has. So what we get in this setup is that in addition to our common analyzer implementation class, in another package called Juice, because it's Juice-specific configuration, we get this common module class containing the configuration that we just saw. And in our module descriptor, we now need to export this Juice configuration. So this configuration can be loaded later by our CLI code. And we need to open the package that contains the implementation class, because the dependency injection framework needs to be able to reflectively instantiate it. So it's a bit different than what we saw with services, and it's a bit more elaborate. And you also see that, of course, we need to require our API module, because we need to know about the analyzer interface, and we need to require Juice and the Juice multi-bindings jar as a dependency. And the reason why we can do this is not because Google Juice is already a Java module, but that's because of a different feature, which we won't go into now, but it's called automatic modules. And automatic modules allow you to take a non-modular traditional jar from the class path and put it on a module path, and it will behave as if it is a module. It will just export all of its packages, and it will have dependencies automatically on all other modules. So it's not a very good module, but at least you can use libraries that haven't gotten a module descriptor yet in your system. So we take advantage of it this way. And in our consuming side of things, so in our CLI code, we need to instantiate Juice with create injector. And in create injector, you need to pass in all the configurations of the dependency injection that you have in your different modules. So we have the common module, the Kincaid module, and then finally we can ask the injector to get us an instance of the CLI class, which will be injected automatically with our services from the different modules. And the CLI class looks at this, and we can finally use add inject on our constructor. Wow. That's pretty rough road, right? I mean, it's a lot of the concepts to take in, the open packages and the configuration that we need to export from each provider module that can be used in the main modules. So I will definitely admit this isn't a walk in the park. And frameworks like Juice and Spring, they will be working towards support for the Java module system. And it will look something like this, but I'm not entirely sure whether this is the end of the story. But anyway, what happens now is that in this common module, we create this binding, this configuration using the Juice module, Juice automatic module. Then from our CLI module, we require this algorithm common module because we need the configuration to instantiate our injector. And once we have that, we can create the injector in Juice, and we can finally get our injected instances. So this doesn't feel very good, right? Because what happens is that we still need to require these two implementation modules because the dependency injection configuration lives there. And we need access to this dependency injection configuration to bootstrap our dependency injector. And when you think about this, it makes sense, but we don't really think about this because we use dependency injection frameworks now on the class path, and they can just reach anywhere in your application and it all works by magic. But actually a dependency injection framework is really, really, really invasive if you think about it. It hits almost all of your code. And that's something that you find out when you try to modularize your code, because modularizing is all about creating nice boundaries and saying no to other code. So that's sort of a trade-off if you are going to use dependency injection with the Java module system. But we can do better than this, fortunately. But before we look at an improved situation, so what are some of the benefits of using dependency injection? Well, you can use the add inject annotation, right? And not use the unfamiliar service loader API. And of course, this is a good argument. I mean, it will be a hard sell to move everybody to the whole service loader setup, and it feels a bit low level as well. So I totally agree that this is something that you really want in your code. On the other hand, we saw in our solution just right now that we still, when we use dependency injection, aren't as decoupled as in the services situation, because we still require these implementation modules for their dependency injection configuration setup. So still, if we add analyses to this system, we need to update the configuration, and we need to recompile our CLI module. So that's not very nice. And another thing that might not be a big deal, but depending on how you view it, it might be, is that we have all this dependency injection configuration going on in code, whereas the services provides and uses configuration is declared in the module descriptors, and the module system actually helps you in wiring these providers and users together. So that's something where we don't get help from a dependency injection framework, but we do get help from the services mechanism. What if we would combine the approach of using services and still use dependency injection? What would that look like? Well, we can do that. So if we look at this common implementation module that we saw a couple of moments ago, we had this exports line for the juice package containing the dependency injection configuration, which really trips up our whole setup, right? So we want to get rid of this exports, hopefully. And we can do that because instead of exporting this class containing the configuration, we can of course also offer it as a service. So we're going to offer it as an abstract module. And this also shows that a service type doesn't have to be an interface. It can also be a abstract class or even a concrete class, although it doesn't really make sense in most cases. But this type comes from the Google Juice library, and we can use that as a service provider type. And then we provide it using the common module, the configuration module that we had inside of our implementation module. And then we can actually drop the exports clause. And on the other side, on the consuming side, we had these nasty requires on our implementation modules just to get the dependency injection configuration. And we can drop these as well and switch them out by saying, okay, we're going to say to the service mechanism that we are interested in all instances of abstract module that have been registered. And, oh, there we go. And now we can do a service loader load call in our CLI to find all the abstract module configurations, pass that to our injector, and then we're up and running again without having the tight coupling between the service provider modules and the service consumer modules, and still use the add inject. So this is a pretty long way around, but it really drives home how powerful services are, how they can help you in really decoupling modules, and how you can also use dependency injection in the modular world. Now, there's also design concerns that you need to think about when moving to modular development in Java. And these are not all really groundbreaking or new, but it's definitely something that you will be thinking harder about when you're moving to modules. So the first thing that you'll run into is that you need to name modules. And naming can be hard, we all know that. So a distinction that you should make is a distinction between application modules, and these application modules, they should have short and memorable names, like the ones that I've shown, easytext.cli, for example. So project.component is sort of the template that we use there. And in this way, you can easily recognize the functionality in your system, see how it all works together. On the other hand, there are some modules that you might be creating that are more widely applicable. Let's call them library modules. And their uniqueness is much more important. So what you want there is to have a unique name. And we also already do this for packages, right? We do sort of the reverse DNS notation. And we should apply the same reasoning to module names, at least for library modules. So what you would do there is take the root package name. So that's the longest shared prefix of all packages that are inside of the module, and take that as your module name. And this way, it will be uniquely reusable across the whole Java ecosystem, and it will be easy to tell that it's your company's library, etc., etc. And probably if you have a library published on Maven Central, you're already using this sort of setup, using the group ID and the artifact ID combined together. Now, there's different types of modules that we can think about. And one that we saw already is the API module, which contains, for example, our analyzer interface. Now, when would you have a separate API module? Well, the reason why I did it in our example is because we have multiple implementations of this API. We had multiple analyzer implementations. But it isn't always the case that you expect to have multiple implementations. So it's a very valid pattern to have modules that bundle an API that is exported together with their implementation that might be offered as a service or be used through dependency injection, doesn't really matter. So you can also have a module that combines these. And that doesn't mean that the implementation that's bundled has to be the only implementation, right? There can be more. It's only we sort of have a default implementation available in a single module that also exports the API. So that's the trade-off that you make there. Now, we've seen an example of interface being part of an API module. Now, of course, an interface refers to other types in its method signatures. So these types, this can be data objects, these can be enumerations or other things, exceptions. These should all be part of the API module as well. Everything should be in there for other modules to be able to use your API. Another discussion that you will run into when defining module boundaries is how big should these modules be? And if you go for the very small module route, you get really tiny modules, all with one purpose, sort of the Unix philosophy, right? Doing one thing and doing it really well. And this will give you nice composability characteristics, and you can reuse these little pieces everywhere. But at the same time, it's very hard to make sense of a system that consists of hundreds or thousands of components, of modules. So on the other hand, there's something to say for making bigger modules and making them more usable from the end user perspective in that way. And the nice thing is that you don't really have to choose. You can get the best of both worlds with a concept called aggregator modules. So what you can do is that you can create a sort of aggregator module. In this case, we call it mylib. And it does requires transitive of mylib 1, 2, 3, so where 1, 2, and 3 are the components of your library. And this transitive keyword ensures that anyone who will have a dependency on mylib will also automatically get a dependency on every part that's mentioned there in the 3 requires. So if we make this visual, here we see this mylib with the 3 requires transitive edges to its parts. And this aggregator module, by the way, doesn't have to contain any code. It can just be empty and only have a module descriptor. Now, if we would have an application module that depended on mylib, it would, through these requires transitive edges, automatically get what they call implied readability on all 3 of these submodules. So that's a very nice pattern. And at the same time, application can also still choose to only depend on one of the parts that are under the aggregator module. You don't have to use the aggregator module. It's just a convenience that you can offer to the outside world. You can apply the same pattern in a different way, where you, for example, say, I have some core functionality and I have some extended functionality, and the extended functionality builds upon the core, so it has a dependency on core, but it is a transitive dependency again. So if your application would have a dependency on mylib extra, it will also get implied readability, a requires relation, automatically with mylib core. But as an application, you can also choose to only get a dependency on mylib core, if you know that you are only going to use the functionality that's in there. And in a modular world, it pays to be very precise in your dependencies. So you could just say, okay, I'll just depend on every module that I can find. But it doesn't really help you in creating more insight into your application. And also, all the tooling around the module system works on the module graph of your application. And the smaller it gets, the more advantages you will get from that as well. If you saw my previous talk about linking, for example, if you have a small module graph, you will get small custom runtime images containing only the modules that your application needs. Another thing that's different between jar files, traditional jar files, and modular jars is that traditional jar files, they can have cyclic relationships. No problem, that just works. Modules, on the other hand, cannot have cyclic relationships. This is implemented inside of the module system. There's a check, it checks for cycles at compile time, and if there are any compile time cycles, then it will just not compile this for you. So what to do if you want to take your existing code, which is distributed across two jar files in this case, and we have an author class and a book class, and apparently they need each other. And what we see here is that the author has a list of books, and the book has an author, so this is a classic circular dependency that's going on here. Now, this is not something that you can automatically fix by running a tool or something like that. This is a design question. This is something that you will need to think about. And of course, there are many ways to break this cycle, but I'll show one of them to you. So we can observe that the only reason that book has an author is to get the name of the author while printing the book. Now, this points to a new abstraction. So what we could do is, for example, in the books jar file, in the books module, add a named interface containing the getName method. Now, if we have the author class implement this named interface, then we've broken the cycle, because now only the author depends on books, because the named interface is in there. The book only has to care about the named interface, because it calls getName, and it doesn't really matter what else is in the author. It's only interested in this abstraction. And the other nice side benefit of this is that in this case, we don't even have to export the author class anymore, because book doesn't really need to know about author, it only needs to know about named. So in this case, author will implement the named interface. It will still have the same getName method that it had before. Nothing changes there. It just implements a new interface. And the interface named lives in the books module. Or it could live in a separate API module, depending on how we plan to use this. But again, this is a design decision that you need to make. And this is not something that can be automated for you. You really need to think here for yourself. Another pattern that we see a lot in applications, and especially in frameworks, is that they can have optional dependencies. So what would happen in the class path situation is that you would run your application, and if you would add some jar to the class path, then it would be picked up by the application or by the framework. But if it isn't there, then it would run fine as well, and just would have some degraded functionality or be slower or whatever. So how would you model an optional dependency in the module system? Because we so far have only seen the requires keyword, and if something is required, it's always required. It's required at runtime, at compile time, etc. So what you can do is you can try to model optional dependencies using the so-called compile time only dependencies. So you can add the static modifier to the requires keyword here. And this means that the fast JSON-lib library in this case must be present at compile time when compiling the framework, but at runtime it's optional. So if you leave off the fast JSON-lib from the module path, it will still run fine. Of course, that means that you are responsible for avoiding runtime exceptions in your code. Because now, if you're going to use any type from this fast JSON lib, you need to do it defensively through reflection, like this. So you get the class using class for name, then you instantiate it, and then you're finally using it. And if it's not there, you will get this reflective operation exception, and you need to have some sort of fallback there. So this isn't very nice, right? And if you have this with one type, it's sort of manageable. But if you have to do this for every type that you're using from an optional library, then it gets very hairy. So what you should do, if you can, of course, it depends on the design of your application and how much influence you have over that. But better is to use services. So what if, instead of requiring this fast JSON lib implementation, the framework would require some JSON API module, and then say, okay, I use this JSON API.json implementation, and then at runtime you would just use the service loader to find the implementation of the service if it's there, and if it's not there, well, then you can just fall back after find first. You can do or else, and then do something else. And this is, of course, a much nicer way to work with optional dependencies. But again, whether you can do this really depends on the amount of influence you have on the consuming and the producing side of the optional dependency. So if you can't do this, then you're still in the require static world, and you will have to code defensively, like you probably already did before if you used optional dependencies. So another issue that comes up a lot when talking about the module system is the question of, okay, so that's nice. We have this module path and we put modules on it, and together they form the application. But can we also add modules at runtime? And this question comes especially from people who are used to OSGI, which is a dynamic module system for Java. And there you can just hot load new bundles, they call them, the modules. You can hot load new bundles into your application, and you can start using them right away. And the question is this also supported in the Java module system? Now, before we can answer that question, we need to explore the notion of module layers. And this is something that you won't directly run into if you just start using modules, as we've seen so far, just putting them on a module path, etc. But you will need to know about this if you're going to answer the question of dynamic module loading. So what we see here is that we have, for example, a module path containing all our easy text modules. And if you would run this, then at runtime, what happens is that the module system instantiates a module layer containing all these modules. And a module layer is only instantiated if it can satisfy all the dependencies, etc., etc. So this will be a well-formed graph of modules inside this layer. But there's always one so-called boot layer that's constructed from the module path. Now, this boot layer is immutable, so you cannot add any modules to it anymore. And this boot layer contains all the application modules that are on the module path. It contains all the platform modules, so the modules from the JDK that your application uses. And in this boot layer, you can only have a single version of any given module. So that sort of seems to indicate that it's not possible to dynamically load modules because, well, it's immutable, you can't add it, and you cannot have multiple versions, so that's not going to work. Well, not automatically, no. But you can yourself create new layers on top of this boot layer at runtime. And these layers together form a hierarchy. So you could, for example, create a more empty boot layer by leaving off our implementation modules, our analysis implementation modules. So we would only have the API and the CLI and the GUI module, etc. in the boot layer. And then we, at runtime, would create a new layer, loading, for example, the callman module. And any new layer that you create needs a parent. In this case, the obvious parent is, of course, the boot layer. And what happens is that this callman module gets resolved, and it can also reference modules that are in the parent layer. In this case, in the boot layer. And of course, that's necessary because callman requires the API module, if we remember the example. So this way, it all works out. And this doesn't just work for a single module. No, a layer can contain multiple modules, which together should all resolve, right? All the requires statements should be satisfied. And it again has a parent and can resolve against the boot layer. And the nice thing is that a new layer that you can create can contain another version of a module that's in a lower layer. So you can sort of override module versions in this way. And all modules in the newly created layer will see the new module version. Now, I want to show a little demo of this, where we see this dynamic loading in action. And for that, I'm going to switch to the easy text example that I've shown in my first talk as well. And we're going to do a checkout of the dynamic loading branch. So what we have here is we have the API module containing the analyzer interface. We have two service provider modules. So Coleman here, for example, just provides the analyzer interface with the Coleman analyzer implementation class. And we have a Kincaid provider class. We have a CLI and a GUI setup. And what we're going to do in the case of this example, is that we're going to compile and run the application without these two provider modules on the module path. So if we do that, we should get a UI. There we go. And you can see there's no algorithm available yet. Now I added a button which reads, there we go, add analysis. And we can point this to a directory containing the modules for a certain analysis. So we can, for example, add the Kincaid analysis, and it needs some other modules, and these will all be resolved. And I click open, and you see that dynamically this module has been loaded into a new layer, and it's now available as a service provider, and my code can use this code. And I can do the same for the other analysis that we have. So here you see that it's actually possible. Now we have two analyses. It's actually possible to load modules at runtime and to add them to our application that's running without any recompilation, restarts, or whatever. Of course, you would like to see how this works. So let's go to the implementation. And what's interesting to see here is that we still use the normal service loader API. So let me make this a bit bigger, like this. We still use the service loader API, but what I did is I added a second button where we choose the directory. And if we get a directory, we call the load analysis in layer method, that I'll show shortly. And there you can see that we get back a new module layer. And now we can call service loader again, and we pass in this new module layer, and we say we want all the analyzers that are part of this new module layer. And then for each analyzer that we find, we add it to the UI, and we update our UI. So now the last piece of the puzzle is, of course, the load analysis in layer module. And you'll see that it's quite involved. So this is not a API that you would be expect to use a lot in your module system adventures. But if you want to do this, then you can. So first you need to construct a module finder, which maps the modules from the file system to something that can be handled. And we just pass it our directory path. Then we need to create the parent layer, or actually find it because it's already created by the JVM. And we just call module layer.boot, gives us back the parent layer. Then we need to construct a so-called configuration, where we say, okay, resolve and bind all modules that are in the module finder. We won't discuss this now. If you want to know the details, read the book. But what happens here is that it will find all service providers that are part of the newly created configuration, and it will bind those for you. And last, we invoke define modules with one loader on the parent layer, and this gives us back a new layer. And as you can see, you also need to pass in a class loader, and this is a class loader that will be the parent of the class loader that gets created for the new layer. So again, this is quite an advanced API. You need to know about class loaders, you need to know about the module system, etc. But it is possible to load new code dynamically into a running Java module application. So that also brings me to the end of this presentation. I do think you will have many questions left, so we have a few minutes. But also, I would like to raffle this book. So what you can do is you can follow me on Twitter and tweet at me if you want to have the last copy of the book that I have with me for now. I also have some Pluralsight courses that you can have a look at. If you don't have an account, come on up here and I have a free month of Pluralsight for you as well. And if there are any questions, I'd be pleased to take them now.
One question, maybe it's a silly one, but could you show the descriptor file one of you created, which uses keyword uses?
Sure. So. Interesting. Give me back my. Where is it? That's what I'm going to do. So, you said where we have a users or provides?
Users or provides, because there is one simple question.
Yeah, so if we look at, for example, the CLI module, it has a users.
Yes, and I just wanted to ask about Java modularity keyword in this, let's say, package, because it's not in a package in a project. So this is keyword or something?
This is actually a package name. So it starts with Java modularity, easy text, algorithm, API. It's just an example, so it could easily be com.foo.bar or whatever. It's nothing special. This is not a keyword. Only this is a keyword. This is.
It was not obvious for me that the Java modularity word was not present in a package. Maybe I did not spot it, but.
Okay. Yeah. So looking at the structure, you see that the package structure actually starts with Java modularity, easy text, CLI, and that's sort of the structure. So, yeah, okay. Any other questions?
Yeah, about the no-args constructor.
Yeah.
What if we want to use a singleton, or if we...
Yeah, so the question is, what about the no-args constructor for the service? And that is one option. What you can also do is you can provide a static no-arguments provider method and provide that in your provides with class. And then it will use that method, and that method you can do anything that you want. You can instantiate a singleton or just instantiate every time it's called, and that's really up to you. So you have two choices there. Yeah. Any more questions?
One more question about the Java 9. I heard that this is short-term version, then the version 9.10 will be the long-term one.
Yeah, so good question about the release schedule of Java. So around the same time that Java 9 was released, they also announced that they were going to move to a 6-monthly, so twice a year release schedule for major Java releases, meaning that in March we get Java 10, September we get Java 11, and so on and so forth. And it's true that Java 9 doesn't have the long-term support label. So Java 8 has that, and it's expected that Java 11, so September next year, will also get that label. But actually, I mean, the module system in Java 10, 11 will be mostly the same as what is in Java 9. So if you plan to move to a next version of Java, it really makes a lot of sense to already start using Java 9, at least in development. You might not want to go there for your ops, because maybe they only want the long-term support releases, etc. But I do think that if you're serious about moving to next versions of Java, then you would be very unwise to wait until Java 11 or 12 or whatever. I would do it right away, because there's so much that has changed in the modular JDK that will affect your application. So yeah, it is not long-term supported. Then again, it's not a experimental release or anything. It's just, it doesn't have the commercial support label of Oracle. Yeah.
What if I wanted to choose the implementation of the service by annotation qualifier? I would have to open that. Because when I want to find the exact annotation,
Yeah.
to check by reflection, what is the...
That's a good question. So he's asking, how do you inspect any annotations of this service implementation class? And the nice thing is that you can access the class instance, so to say. So not the actual class. You cannot instantiate the class itself, but you can look at the class instance of something that isn't exported. That's fair game. And you can also ask the annotations of something that's not exported. But the moment you try to instantiate it, so you try to create a real object from this class instance, then the module system will say no. So what you get back from the service loader.provider description is an actual class object. And you can inspect the annotation on that. Yeah, and you can even see which methods it has, etc., etc. It's just that you cannot instantiate or call it if it's not exported or opened to you. Yeah. Okay, I think it's time to stop. So thanks again for coming, and I hope you enjoyed it.